Hi, I'm Phil Kopelman, and I'll be talking about a safety case plus SPIs metric approach for self-driving car safety. To get started, the big picture here is that I think you need multi-scale metrics and feedback loops. It's not enough just to do a design hazard analysis. It's not enough just to do an operational risk mitigation. You also need to plan for lifecycle discovery of surprises if you're going to build and deploy self-driving cars safely. The key to all this is understanding and implementing safety performance indicators, SPIs, SPIs. SPIs go beyond vehicle acting unsafely. They go beyond real-time dynamic risk measurement, and they get into the core of validating whether or not the safety case, the safety argument you've made that you're as safe as you think you need to be, is actually true based on feedback data from all phases of the life cycle. Let's start with traditional hazard analysis. A traditional hazard analysis goes something like this. There's some risk analysis, and the risk analysis lists all the applicable hazards, all the hazards you can think of. It characterizes the risk for each hazard. It decides how much mitigation is needed for each risk, and then it documents that all risks have been acceptably mitigated. There are various techniques to create the hazard list. You typically start with lessons learned. The engineers designing the system know some of the hazards. They just know it because they've seen it before. For sure, those should be entered in. But there's also brainstorming and analysis techniques, HAZOP, STPA. Bring your own favorite approach, bring several of them. At some point, you end up with a big list of hazards, and then you have to document they've been adequately mitigated so that the total system safety is acceptable. There's a limitation, though. You can never think of all the hazards. Despite all the lessons learned, despite all the brainstorming, you'll hopefully get most of them, but you can never quite get all of them. And even if you did get all of them, the world will change tomorrow, and there'll be a new hazard that didn't even exist today. So there's always some aspect of incompleteness to hazard analysis. For sure, you want to be responsible and get the ones that you should get because they're obvious, or you've seen it before, and so on. But at some point, you'll never be perfect. In traditional cars, that's generally lumped in with, well, we have a human driver who's responsible for safety in the end. So as long as the human can mitigate the risk on the fly and to get the vehicle to a safe state, then it may be okay that we have unknown hazards that were just unreasonable for anyone to think of. Now let's get to ADAS, Advanced Driver Assistance Systems. With an ADAS system, the driver is still in charge, but now the scope of the hazard analysis is not just a piece of equipment is malfunctioning, but rather includes the uncertainty and changing nature of the external world. You're operating in an open world. All hazards are not going to be known, and new hazards will appear. So this is going to be much more difficult. You can't simply sit down, do some analysis and say, yeah, we think we have the hazard list, we're good to go here. You actually have to do some experimentation in the real world to even uncover some of the hazards that you just never would have thought of. This is handled with safety of the intended function, SOTIF. The idea of SOTIF is you operate in the real world, you observe triggering events, so these are things your system is not able to handle as well as it should. The intended function does not work as you intended. You mitigate the discovered hazards, and you repeat. And you keep running a loop over and over until you've mitigated all the hazards you can find given a target for how safe is safe enough to be ready to deploy. From a pictorial point of view, you have a design and there's a loop for hazard analysis, but there's another piece which is the testing, and then that feeds sort of triggering events back to the design so you can design in mitigation and make sure your total vehicle level risk is acceptable. This one has a limitation of unseen triggering events. Here, when you're operating the real world, it's very unlikely you will encounter all the weird things that will happen for a full-size deployed fleet. So you're not going to get all the triggering events, but you hopefully get enough that it's responsible and acceptably safe to deploy. In the end, a human's responsible for system safety. This is driver assistance. It is not a self-driving vehicle. So in the end, the human is responsible for system safety, and hopefully you've designed a system where that's a realistic ask to make of the human. The bigger picture is, if you have a non-self-driving car, if you have an ADAS car, for example, it looks like this. You have design, which has hazard analysis. You have testing, which has sort of triggering events. And during deployment, your risk mitigation mechanism, your primary one, is driver experience. The driver is able to mitigate any unmitigated hazards that have escaped out into the deployment. And the driver learns with experience, so the more experience they have, the more likely they are to be successful at mitigation. However, at some point, there are things that drivers simply cannot mitigate. And there are some tasks that drivers are bad at, for example, continued high vigilance when nothing's really going on. So the other thing you're going to see is there are going to be mishaps in deployment. The driver will do dynamic risk mitigation, but there are going to be recalls for technical faults that it is impossible or unreasonable for a driver to mitigate. Recalls are never supposed to happen, but they do happen all the time because of technical faults in system design. That's not going away when you have ADAS, and so you can expect to see some more recalls going back to design. Currently, this is the world we live in for pre-self-driving cars. And the question is, what happens when that driver goes out of the loop? There's no driver to monitor and mitigate the risks at deployment. And the answer is kind of subtle. You not only need a runtime mechanism, but you need to think hard about that recall arc and turn it into something more subtle and something less risky at runtime. So let's look at hazard analysis for full autonomy. You still have an open world with unknowns and changes, just as you did in ADAS, but now there's no human driver to take care of the loose ends. If there's a hazard you didn't think of or did not encounter during testing and validation, the driver used to be responsible for that, but now your autonomy is responsible for handling something it's never seen before, and that's something that autonomy struggles with. The approach I like for this I call positive trust balance, and that is a way of saying trustworthy positive risk balance. Positive risk balance is generally the idea that you should be at least as safe as a human driver. I would argue you want to do better than that, and I'm not saying positive risk balance is the only way to go, but I'm using it as an example here. If you want to not only say, I think I have positive risk balance, I'm safer than human, but in fact, be really sure that that's really the case, you need more than just some simulations saying, yeah, it looks okay in simulation, we're probably okay. That's not enough. In fact, you need some pieces. You need to build it right, you need to test it right, you need to improve it right, you need to live it right. And what that boils down to is you need not only validation, but you also need good engineering. Sure, you need good validation. Of course you do. You also need a strong safety culture. But the thing I'm going to concentrate on in this talk is the field feedback to handle surprises. You need the feedback from the field or you're not going to achieve your lifecycle risk target. Positive trust balance is an excellent fit to the UL 4600 safety standard, which requires a safety case. 4600 has SPIs built into it. It has feedback built into it. And so everything I'm saying is a good fit for UL 4600, although the rest of the talk is about the feedback, not about the standard. All right, if we're going to use safety cases, let's take a minute to talk about what they really are. A safety case is an argument that has a claim, which is some claimed property of the system, such as the system avoids pedestrians. An argument, why this is true. For example, well, we avoid hitting pedestrians because we detect them and maneuver to avoid. And some evidence to support the argument. Tests, analysis, simulations, all of this is evidence. Typically, it's a fairly detailed argument, and so you can have subclaims. You won't just say, well, I detect and maneuver to avoid. Well, we have to break it down. We detect pedestrians. Here's our evidence that we detect pedestrians. We maneuver around them once we're detected. There's our evidence for that. And then, by the way, sometimes you can't maneuver around, so we stop if we can't maneuver, and there's evidence that that works. So all the evidence supports a claim, subclaims, argument trees, all the way up to the central claim, which goes back to we're as safe as we need to be. So the context of all this is within a safety argument, where the claims are the things you're saying, that's what we think we do, and the argument is that's why it means it's safe, and the evidence is this is why our arguments make sense, because they're based on actual evidence. Let's revisit the feedback model now to talk about self-driving cars, and this is the default one. It's not necessarily the one we want. The safety case argues acceptable risk without a driver. Perhaps it's positive risk balance, perhaps it's something else. For our purposes, it doesn't really matter. That's just a placeholder. But at some point, you've decided what acceptable risk is, and you're trying to argue that you've achieved it. Here's the picture. We're back to there's design and testing and deployment. And the safety case fits into, traditionally, it couples to design and test, and it argues the design's acceptable and the testing shows the design's acceptable. The design produces hazard analysis that goes to the safety case retains a hazard log, a list of all the hazards, and the loop is closed by updating the design until the hazards have all been addressed. And the testing includes not only making sure the hazards actually have been mitigated, but also a set of triggering events. And the deployment will be incidents and loss events. Now, the issue with this approach, which is sort of the default if you just kept doing business as usual, is that there's no driver to mitigate risks at runtime. And so you're waiting for a crash or an incident before you actually know something's wrong in your deployment and you update the safety case. And you really want to do better than that. You somehow want to know that something's going wrong before it's likely that there's been a crash. To do this, we use safety performance indicators, SPIs. The idea of a SPI is that it attaches to a claim in a safety case. So here's a safety case where I'm only showing the claims. I'm dropping out the arguments and evidence. They still have to be there, but for this graphic, all you're seeing the claims. The top level is the vehicle is as safe as it needs to be acceptably safe. The next level is we get there by doing a bunch of things, and one of them is avoid crashes. And to avoid crashes, we do a bunch of things, and one of them is we detect objects. And to detect objects, our sensors need to be effective as well as a bunch of other things. And to be effective, our sensors need to actually be clean if they're an optical sensor, because if they're full of mud, they're not going to actually see anything. And for data fusion, it has a bunch of things to be effective, but also, by the way, the software actually has to be written properly, and we have to have good test coverage to confirm that. So this is an abbreviated version of a safety case from up at the vehicle level down to not only the subsystem level, but also the engineering process level, the maintenance level, the inspection level. All those things have to be there, because if you're missing one, then you're not safe. SPIs attach to the claims of the safety case. So you can have a SPI for a vehicle safe. At some point, you know what your risk target is. You have a way of measuring it, and that's what that SPI is. But you don't find that out, so you deploy the vehicles and see how it turns out. For sure, you want to be keeping an eye on that so that if it's out of whack, you find out what's wrong. But that isn't the only measure you need, because you won't know that till after you deploy. And avoiding crashes is sort of the same way. So you can put SPIs lower down. You can say, well, let's put a SPI on detects objects. Let's have an idea of what our object detection performance has to be to result in an acceptably safe vehicle. You sort of need to know that to have a valid safety argument, and if you know that, you should be able to measure it somehow. Well, to detect objects, you know you need sensors are effective, so you should have a measurement on what it means to be effective and data fusion effectiveness. Now, those are the sorts of things that you might measure during tests, during simulation, during operation. But some SPIs are more than just operational metrics. For example, you might have a sensor cleaning SPI. If you say our sensors are effective because they're obscured by dirt and mud less than 0.1% of the time, and I'm just making up an arbitrary number there, then you really want to know whether you're at 0.1% or 10%. Well, a SPI can tell you whether or not your assumption that you met that target is valid or invalid. Software quality. You need a low defect count for safety critical software. Well, what's your defect count? And if your defect count is too high, then you're not as safe as you thought you were, and so on. When you look at this picture, what you realize is that the lagging metrics, the metrics you don't get to measure until you're near deployment or your system is built and you're doing vehicle level testing, those live at the top. But the leading metrics, the things that predict how the other ones will turn out, are down at the bottom. So the leading metrics, you can know many of them at design time before you've ever taken a mile on a test track, and you have an idea of where you are, where you think you need to be, whereas the lagging metrics come out later. So the idea here is to take a safety case, and in principle, every single claim and subclaim of the safety case, if you can figure out how to measure it, you attach a SPI to it. So you're not monitoring just whether the vehicle is safe. You're monitoring whether or not your safety argument is actually true, or there's something wrong about it, that you argued something but it's not really true. And that's what the SPIs do for you. Let me do some examples of SPIs, because it's a somewhat abstract concept in the last picture, but let me give you some examples of how these work out at different levels of abstraction in the safety argument. When people think about SPIs, they often think about, well, acts dangerously. Clearly, getting too close to a pedestrian, closer than you intended to, and having a near-hit situation with the pedestrian, that's the kind of SPI you want to be paying attention to, as well as whether you're tailgating all the time. But those kind of SPIs are lagging metrics. You don't get to find out till you start operating. And they don't provide a way to get insight into whether you're on the right path until after you have some near-hit experiences. But components also have safety requirements they need to meet. For example, if you have a sensor, it probably has a specification for false negative and false positive detection rates. You're designing to that rate. Well, a SPI tells you whether you're really getting it when you're doing track testing or simulation or even unit test in the component. You may have a requirement for no correlated sensor failures. So you may say, all right, I have a radar, I have a camera, and one of the two will see everything I care about. And so if both of them miss something, that's a huge deal. That's going to affect safety, and you should not have to wait until you're out doing road testing to know whether or not there's some objects that are an issue for that kind of sensor failure. Sometimes the context matters. And so you may have a system, and we found this in a real system, that is really good at finding children when they're alone, but when a child's next to an adult, they're misclassified as a handbag or a package or something like that. That's something you really want to know about, and you do not want to have to wait until a child runs in front of your car to find out that you didn't actually see the kid because they were next to an adult. SPIs also extend into the life cycle. They're design and life cycle considerations. The design process has quality targets. If you have safety-critical software for life-critical applications, it needs to be high quality. If you have low-quality software, then you're never going to get yourself to acceptable safety, and you don't need to wait till there are incidents at a vehicle to know that you have issues with the software. You can find that out much sooner if you have SPIs monitoring it. Similarly, there's maintenance and inspection defect rates. If you have maintenance procedures that are required for safety, for example, cleaning sensors, calibration, things like this, and inspecting to make sure the maintenance has been done. If your maintenance is causing problems, that your calibrations are off, if your system drifts out of calibration sooner than you thought and you need to increase your maintenance rate, you should be paying attention to those before you have a loss event. And you can do that with SPIs. You can say, well, we have a target for how often a calibration fails. We have a target for how often maintenance is done improperly. It should be a very low target, but in the real world, it's never zero. So you say, our target is this very low number, and the SPI monitors whether you exceed that number, because if you do, you just invalidated your safety argument. The point of SPIs is, if it's relevant to safety, regardless of whether it's design, operation, life cycle, if it's something that if it's gotten wrong will impair safety and call into question whether you're safe enough, that needs to be in the safety case. And if it's in the safety case, that makes it a claim that you've done the thing you said you were going to do. And if it's a claim, it can and should be measured with a SPI. It's common in self-driving car design to focus on KPIs, key performance indicators. And SPIs are a little bit different, safety performance indicators. And so I'm going to explore a little bit about what the difference is and why you need to use both. Let's take a simple one. You have a distance to an object. The KPI might be the average distance and the variance of the clearance away from the object. And you may say, I have a particular object and my desired distance is 2 meters away as I pass it, plus or minus 10 centimeters as one standard deviation. Having that KPI is great, and it gives you an idea if the car is working the way you think it should work. SPIs are somewhat different. SPIs are not about whether it works the way you want it to, because the KPIs can often be kind of squishy. Is 1.9 meters okay? Well, maybe. It all depends, right? Who knows? Is 0.1 meters okay? No, probably not. But the boundary between far enough away and too close is usually a bit fuzzy in a KPI because it's more about averages and distributions. It's not really about safety. That's what SPIs do. SPIs are, it's nice that you want to be 2 meters away. It makes everyone feel comfortable. That's the desirable performance. But in the end, we're going to argue you're safe enough as long as you're always exactly 1 meter away or further. 2 meters is great. 1 meter is the minimum. 99 centimeters, nope, that's unsafe. There's a hard line at 1 meter. You have to be 1 meter away. And that's a SPI. If you want to go statistical, you could say, well, you have to be 1 meter away 99.99, a bunch of 9% of the time. You're only allowed to be close to the meter once every so often to maintain our risk budget without being excessively risky. So KPIs are about, is the vehicle behaving the way you want it to? And SPIs are about whether or not it's violating thresholds that make you unacceptably risky. For sensors, a KPI might be the detection rate and the signal-noise ratio, because those characterize whether your sensor is behaving the way you want it to. But the SPI is going to be much more about whether or not you have multi-sensor correlated detection failures, whether you lose calibration in the middle of the mission rather than the calibration holding till the end, those sorts of things. For pedestrian perception, KPIs are probably accuracy, precision, recall, things like this, the usual suspects that you see when measuring perception. But SPIs are much more about false negatives. For example, if I have 10 or 20 false negative frames in a row, that may make my target tracker misbehave because it assumed you'll only drop 1 or 2 frames in a row. And so the SPI is about whether you've invalidated the argument for why your pedestrian perception is safe, which is a little bit different than the performance. Another SPI is going to be systematic underperformance. Typically, your safety argument is, I have the following performance for my pedestrians, and I never get worse than a certain amount on any systematic basis. Well, if you have data that says, well, you do great on average for people and strollers you do terrible, but there's so few strollers, the average still looks good, your KPI can be just fine. But your SPI for the argument that, and there's no systematic defect that causes certain classes of pedestrians to be at extreme risk, you may find out that the SPI for that is violated because you're having trouble seeing people pushing strollers. There are some runtime monitoring implications. When people think about SPIs, they often think about hooking them up to some sort of immediate response. SPIs and runtime monitors are actually different things. They have similar concepts, just like KPIs and SPIs have some similarities but are for different purposes. Runtime monitoring and SPIs also have similarities, but they're for different purposes. Let's consider a leader-follower situation where you're trying to maintain safe distance. And this is the kind of thing you see addressed by responsibility-sensitive safety, RSS. It's Newtonian physics, and you can use some equations about acceleration and braking and distance and say, this is my minimum following distance, so that even if the lead vehicle jams on the brakes, I'll be able to stop without hitting the lead vehicle. A safety monitor, a runtime safety monitor, would look at this distance and say, oh, we're too close because given an assumption of 1g, 1 gravity of braking of the lead car, and giving my capability of, I'll make up a number of 0.7 g's and so on, we do some math and say, this is how far we have to be away to be able to stop guaranteed with a panic brake under a bunch of assumptions about road conditions and some other things. And so if we're too close, we're going to back off, we're going to reduce speed, we're going to brake or something like that. So a safety monitor in real time, subject to the assumptions of the safety case, says, here's how far away we have to be, and it takes corrective action if you're not. That's important. That should be there, but that's not really a SPI. For a KPI, just to complete the contrast, a KPI is, am I doing best effort separation given the driving conditions? For example, you may want to be the same distance from the car in front as the car behind. You may want to change lanes to give yourself some more room, whatever. The KPI is, am I keeping my separation distance the best I can given conditions? SPIs are a bit different. SPIs are not about, is my car driving the way I would like it to drive? SPIs are not about whether or not I'm too close. I mean, part of the safety argument is you have a safety monitor to handle that, and you want to make sure that's working. But a bunch of other SPIs feel a little bit different. For example, some of the SPIs here will be more about, is the situation more dangerous than I expected? Do I have operational design domain, ODD definition issues? Maybe I argued that, well, it's okay to have an unsafe minimum distance according to RSS as long as I do it less than 1% of the time, and I have these other mitigations, and you may argue, well, a 5 mile an hour impact is something I'm willing to accept every once in a while as long as it's not too often, and so on. But if you're spending all your time in dense traffic when you thought it was only 1 or 2%, then your safety case is wrong because you misdefined the ODD. And so a SPI that measures traffic density to say, yes, in fact, you assumed dense traffic would be very rare, here's the measurement of how often dense traffic happens, is required to maintain validity of your safety case. You may also say, well, lead vehicle will never brake at more than 1G. And you're out on the road and all of a sudden a sports car in front of you brakes faster than that. Yes, that can happen. That breaks your safety case. Your safety case said that will never happen, and yet here we are, it happened. So now you have to go back and revisit your safety case to say, well, what fraction of the traffic will do that? How often will it happen? And so on, to go back and recompute and make sure you met your risk target. So the idea is the SPIs are trying to figure out whether or not the assumptions baked into the safety case are true, because a SPI tells you, yes, you've argued this will never happen, and yet here we are. So that feedback tells you there's something wrong with your safety case. The idea is SPIs measure the validity of a safety case claim. You have a safety case, you have a claim, the SPI takes data to see whether that claim is true or false. Now to be clear, this does not require you to be perfect. A safety claim might be this never happens, but a safety claim might also be this happens less often than once every so many kilometers. If that's true, the SPI doesn't say it happens so you're unsafe. The SPI said, well, you claimed once every 10,000 kilometers, and it's really happening once every 5,000 kilometers, so your safety case is broken because it's not doing what you claimed it did. So again, it's not about perfection, it's about whether or not the average, the statistical number, the threshold, however you define it, is actually in line with what it needs to be to have a valid safety argument. So a SPI value violation, so you say, fine, on average once every 5,000, but on average it's happening every 2,000, that's a value violation. It doesn't meet the threshold you said. That means your safety case is invalid. Does it mean you're unsafe? It might. It's not clear because you might be getting lucky somewhere else, but what it does mean is the argument that you're safe is not valid. So now you don't know if you're safe or not. And in general, if you don't know if you're safe, there's a good chance you're unsafe. You need to do root cause analysis for this reason. When you have a SPI value violation, if the SPI says your claim is not true in the sense that it meets whatever the numeric target is or some other sense, when the SPIs say, hey, your claim's not true, you have to do root cause analysis. And it might be a design process defect. It might be a design defect. It might be a hazard analysis gap. It might be something you missed in SOTIF. It could be training data bias. It could be some problem with your evidence, that your evidence had a bias. Or it might just be an assumption error. You assume something would happen very infrequently and it's happening all the time, for example. So the idea is when you deploy, and even during test and even during design, you measure these SPIs and you feedback to improve your system so that the safety case becomes valid again, which usually involves changing the safety case to conform with the reality that the SPI is giving you. This brings us back to the big picture of the design, test, deployment cycle and how it fits together. The safety case argues acceptable risk, and it's going to have to be connected to deployment as well as testing and design. And the SPIs monitor the validity of the safety case. Sure, you still do hazard analysis. You still do the SOTIF triggering event analysis. You still do something about runtime safety, but now instead of a person, it's going to be the runtime safety monitor, and that's great. So the runtime safety monitor says, well, the external world's doing something to us that's unsafe. We're going to detect that and do countermeasures. But you still need something to feedback flaws, defects, shortcomings, omissions in the safety case so you can fix them. And that's what SPIs do. SPIs feed data from design, from testing, from deployment, back to the safety case. So even though the day you deployed, you had that best safety case you could have based on all the data, there was something you didn't know about. There's those pesky unknown unknowns. One of them rears its head, generates a SPI violation. You go back, you update your safety case, and you improve the system. Wrapping up, you can look for incidents at runtime. You do runtime risk analysis, but that's only part of feedback. Feedback has to happen at all levels of the design and deployment cycle. If you remove a human, in other words, if you have an actual self-driving car where there's no human responsible for safety, then you're going to have to mitigate surprises because you will never catch everything during the initial design cycle. The only way to get to safety is to not only do a really good job designing, but also be continuously monitoring for things that indicate your safety case is not currently true. Tactically, you want a runtime safety monitor so that you can take corrective action in the moment, but strategically, you need runtime SPI monitoring. All the vehicles in the fleet, every time they notice something weird happening, something that doesn't make sense according to the safety case, need to be sending that information back so the safety case can be rechecked, modified as appropriate, revalidated, and the fleet can be updated. SPIs give you feedback on design quality, process maturity, testing coverage, lifecycle procedure execution. It's more than just about runtime behavior. Did the vehicle act unsafely? It's also about if the vehicle acted or experienced something that violates and invalidates the safety case, that needs to go get fixed because otherwise you're just guessing about safety. SPIs are about measuring during the entire system lifecycle whether you're actually as safe as you think you are. Field feedback is a key to SPI success because even if you deploy with a perfect system at the time of deployment, the world will change and you'll have to deal with it using SPI feedback.